On Monday, we just came up with this one picture. There's the tape. There is some zeros and ones on the tape. There is a head that can move left or right by steps of size exactly 1. And there is a state that's remembered, and then we have a Turing machine program. So, and this was from all Turing machine. Right, and of course this is, in many ways, it's more a picture than a definition. That would be a perfectly reasonable complaint at this point. I guess the program here is this finite collection of 5 tuples, right? This is more of a picture than a definition, but slowly but surely we'll observe it again and again. I'm not actually going to do a lot of proving about this, but we'll keep on observing it, and then I'll intimidate you into believing it. We'll observe that the actual details don't really matter that much. And so because the actual details don't really matter that much, I don't really have to go into all that deep a level of detail to give you these details, because just pick what you like. But we did pose an important question at the end of the last lecture. How does a Turing machine compute anything one might care about? It's a perfectly reasonable question. Now, if you happen to care about infinite sequences of zeros and ones, and functions from infinite sequences of zeros and ones to infinite sequences of zeros and ones, where the input and the output differ in only finitely many zeros and ones, then you're all set and you don't have to ask this question. Right? In any other case, you have to ask this question: how does this kind of notion compute these things we care about? Okay, and what is the basic kind of function we would care about? The basic kind of thing we care about are functions from, right, its input is a tuple of natural numbers, and its output is a tuple of natural numbers. And for some of these functions, so we want to say in the end, such a function is computable exactly when there exists a Turing machine that computes it. Currently, certainly not true, because these are sequences of zeros and ones, and we were talking about natural numbers. And so, what we'll have to come up with are reasonable input and output conventions. And now the trick is that of course you can come up with an input convention that says, well, I'm going to represent the nth natural number by a 0 or a 1 on the tape, just in case the twin primes conjecture is true. Right? You could make such a convention, but then you notice that between the natural number and the coding on the tape, there is something awfully complicated going on. In this case, you don't even know how to encode it. So what we're looking for are obviously simple ways of encoding things we care about on the tape. And we want them to be obviously simple because when we are encoding onto the tape, we can't already use Turing machines to decide if it's simple enough, because we're trying to be able to use a Turing machine on an input as a natural number. So we can't do our coding from natural numbers to the right input for a Turing machine using a Turing machine yet. So what we really need is an obvious way of doing this coding such that there's no complexity in the coding. It's completely straightforward. And the same with the output encoding. We don't want an output encoding that does anything complicated. As simple as possible is really the strategy you want. You want something obviously effectively computable, because then it doesn't do any of the computation for you. Okay. So, input encoding. Now, for this input encoding, many choices. Right? And if you make one choice and I make another choice, and both of these choices can be perfectly fine, we still have a problem if we try to communicate, because the Turing machine you wrote for your input encoding will not work for my input encoding. So a Turing machine computes something only relative to input and output encoding. And one of the choices here is to say, well, I can represent a natural number on the tape in unary notation. Right? You might think it's zeros and ones, and so I'm going to use binary. But then how can you tell where your natural number starts and ends? Now you can do something a little tricky to make more interesting encodings. But we're looking for something very simple, and this is certainly a choice which is very simple. And so, for instance, if I'm looking at a function natural numbers, which goes from pairs of natural numbers to natural numbers, the addition function, clearly the addition function should be easily computable, because that's a particularly simple function. And one way I could now say I'm going to encode things is my starting, the starting configuration of my Turing machine is going to consist of the tape, infinitely many zeros going this way. Then there is in unary the first input, followed by a 0, followed by in unary the second input, followed by infinitely many zeros. Now this is still slightly underspecified, because where is the head location? And so we want to add to this that for this particular choice of input encoding for a binary function on the natural numbers, we will include first the one natural number in unary, followed by 0, the other natural number followed in unary, and the head is on the first one in the tape. And moreover, we start in state start. And so now I can say, and my output encoding, the output encoding, I'm just going to make a choice here, and the output encoding is going to be this Turing machine runs for a while. Addition is a total function, so if you have an appropriate Turing machine written for this, then it will always hold at some point. And it holds with the head somewhere, and then there is a number of ones followed by a 0, and in this case, right, it would be 1, 2, 3, 4. This would be encoded by 4. There can be other stuff here, but the particular choice for output encoding I made is look at the head location, then count the number of ones, and then you always get a natural number out of it, presuming there's a 0. But that'll work out because there's infinitely many zeros. I said my Turing machine always needs to hold, so it only touches finitely many cells on the tape, so there always is a 0 at some point, so this is an appropriate output encoding. And so now, with these conventions, I'd have to go and write down a finite collection of 5 tuples which computes addition. And if I do that, then I've shown that addition is computable. Fortunately, I did it on Monday. So the Turing machine program on Monday computed addition. As you may have noticed, and if you didn't notice it, then you go back in your notes and you notice that I run the Turing machine, and the input really looks like this at that time, and the output really looks like something like that, and it really appropriately computed addition. And so that is the proof. Well, I didn't prove it, I proved it by example, I guess. That is the proof that addition is computable, because I was able to write a Turing machine program which computed it using some input and output conventions like this. So that's how Turing machines compute stuff in general. You come up with some conventions about these things, and then using these conventions, relative to these conventions, you can write Turing machine programs that compute things. And there's a couple of standard ones. So there is two standard tricks. First of all, you can make the convention that natural numbers are encoded on the tape in unary, like we did over here. And then once we make this assumption, then from this point on, we can encode things into natural numbers, which have a bit more structure, which makes our encodings a little simpler. For instance, I might want something whose input is arbitrarily finite sequences of natural numbers. And of course, I can do it like here, with sequences of zeros and ones. But I can also say, well, I'm going to encode this into natural numbers, and there we already had a choice for how to encode it on the tape, and so we don't have to do anything new. And as soon as we figure out how to do this, and here there are a couple of standard choices you can do. One of them is something like if you have n0, n1, n2, you encode this by p1 to the n0 plus 1, p2 to the n1 plus 1, p3 to the n2 plus 1, where pn n is an enumeration of all primes. So you can always, with this convention, say that a natural number represents finite sequences of natural numbers, because you can encode like this in sequences of primes, and you get a nice way to represent finite sequences by single natural numbers, which then by our previous convention you can put on the tape. And therefore you can easily talk about functions from finite sequences of natural numbers to natural numbers being computed, computable because we now have a good convention about it. And then the only thing is about writing the Turing machine program, which of course can be hard, arbitrarily hard, right? If you take an arbitrarily difficult function, which is still computable, coming up with a Turing machine program for it would be arbitrarily hard as well. But with this, at least you have some encoding. There's another one which always needs to be mentioned at this point. If I want to just encode pairs of natural numbers, there's the so-called standard pairing function, which, as you can tell, I don't really have memorized, but it's kind of nice anyway. X squared plus 2xy plus y squared plus 3x plus y. And this is a nice pairing function for a couple of reasons. One is that it's a polynomial. Another is that it's a nice bijection. And of course, you notice me picking up my piece of paper in order to write this down. I don't really remember this, but I don't have to remember it. Whenever I need it, I can reconstruct it, because it turns out that it has a nice picture associated to it. this pair of natural numbers, 0, 0, and number 0. Let me see which way we go. This one 1, this one 2, that one 3, 4, 5, 6, 7, 8, 9. Now if I left it at this, then you would, I hope, consider this kind of picture, and a hand wave, look at the bijection I just made, a perfectly reasonable argument for showing that there is a bijection. But now it turns out that this bijection, the nice one from the picture, it is this one over here, the polynomial. And what you want to do is you have this point here, xy, and you wonder, so how many pair is this in this particular enumeration of pairs? And what you do is you look at this triangle here, and what does this triangle look like? Well, right, it's sort of, these are kind of crooked triangles, so it's not really the nicest triangle, but if you go here from x to x plus 1, then you get exactly the number of points that are contained in this triangle, whose area is 1/2 times x plus 1. And then you need the number of points along the line here up to this point, and that's plus y. And either I got it completely correct, or it's pretty close, and you can see how to tweak this formula. But this is equal to that if I got it right. I give it a 50% chance that I got it exactly right, but a 100% chance that if you see this and I didn't get it quite right, then you can tweak it by computing the first 3 or 4 values that were in there. But so these are two standard techniques that are used a lot, and sometimes when you're thinking maybe about like Gödel's proofs and doing things around there, then you actually have to write these things down by formulas. Then this polynomial pairing is often a lot better. If you just worry about computability, you don't really care, because they're both equally nice. Okay. Closer to the triangle clearly doesn't just depend on x, it's x and y, right? So it should be x plus y plus 1. There was something in the back of my mind that was worrying about the numbers of y in this expression, and the numbers of y in that expression, so this is better. Okay. So we also want to deal with much more complicated objects. Right, but as soon as you see this trick for the finite sequences of natural numbers, then really you can see that there is a lot of flexibility, and you can do a lot of nice things. Simple things are like I don't know, binary labeled trees. As long as the labels are natural numbers, then you can think of something like, well, look at this prime encoding, and then you can do something like P1 root label, or plus 1 maybe, P2 encode left subtree P3 to the power code right sub tree, and then you have a really nice encoding for binary trees. That's not one we care about a lot, but last lecture I mentioned graphs and stuff like that, and so you can imagine how to do that. Things we do care about a lot are, well, we care a lot about Turing machines. And now, just in the abstract, out of nowhere, you might be surprised about caring about this, but if you've heard about like Gödel's incompleteness proofs and some of the ideas in there, then you notice that a very powerful thing happens if you can encode the thing you're studying in order to be able to work on itself. Right? In Gödel's incompleteness proofs, one of the big tricks is that he realizes that by trickery like this, you can make natural numbers represent formulas. And as soon as natural numbers represent formulas, then an ordinary formula of arithmetic might say something interesting about the formula. And so that's the big trick in Gödel's incompleteness proof. In our case, we're also going to do essentially the same big trick. We want Turing machines whose inputs are Turing machines. Well, and so then what do you want to be able to encode? Well, for instance, you want to encode, let's call them instantaneous configurations, right? The Turing machine goes along and it's computing, and you would like Turing machines to be able to use as their inputs and their outputs configurations of Turing machines. And so what is a configuration of a Turing machine? A configuration of a Turing machine is whatever is on the tape. Well, with our encoding convention for natural numbers on the tape, there's always finitely much interesting stuff on the tape. And so there's finitely many ones on the tape, and you can encode the locations of the ones as a finite sequence of natural numbers. Then there is which index the head location, so where the head is located, which is again an index of the cell on the tape, and an index can then be add on like maybe to the head of your finite tuple. So there's the head, which is the index of the head of the tuple is the index of the head. The other indices are the locations of the ones on the tape. And then there's one more thing, which is the current state. And the current state, well, right, if you're programming these machines, then you want your state to have nice, meaningful names like start and hold, and I have just scanned the first input and I'm now going to scan the second input, like nice string. But if you're going to compute with Turing machines, then you might as well say, well, there's going to be a finite set of states, so I represent all my states by natural numbers. And then now in front of the head index you can put the state index. And now I've shown you, or I hope I've convinced you, that the configuration of a Turing machine at any point in time can be represented by a finite sequence of natural numbers, which we know can be encoded as a single natural number, which we know we can write on the tape in a very nice and simple way. And therefore, instantaneous configurations of Turing machines can be both inputs and outputs of Turing machines. So Turing machines can compute something about Turing machines. Everybody happy with that? Right? This is the typical kind of level of description you want to do of these things. You don't necessarily want to write down the actual polynomial that's doing the encoding or decoding, because these functions are become complicated. But you want to be able to handwave at it enough to convince yourself, and then if anybody else pressures you, to convince them that you have a good encoding. Everybody happy with that? Instantaneous configurations. Other things which are important to configure are like Turing machines programs. Well, what is a Turing machine program? A Turing machine program is a finite sequence of 5 tuples. Well, if each of these 5 tuples can be represented by a natural number, then the finite sequence of 5 tuples would be a sequence of natural numbers which we can encode. So we only have to worry about encoding individual 5 tuples. Well, what does an individual 5 tuple consist of? I hope I'll pick the same order as I did on Monday, but I give it about 30% chance, 33.333 actually, that I do. No, half of that. Half of, yes. But the 5 tuples, they look something like 0, state, or I guess it's 0 or 1 state, 0 or 1 right or left, another state. Right, and it's easy to remember that the first 2 should be corresponding to the input, and the last 3 should be the output. But then there is many permutations possible there, so my probability calculation was off anyway. But so, if I represent my states by natural numbers, then both of these S's are natural numbers. And right and left, I can clearly just make a choice. 0 represents right, 1 represents left, and then this is also a finite sequence of natural numbers, therefore can be represented as a natural number. Therefore, Turing machines programs can be represented as natural numbers, and therefore as inputs and outputs on the tape. Okay, another nice one, a computation of a Turing machine, right? Because what is a computation of a Turing machine? It is, well, if it holds. Right? If a Turing machine does not hold, then it just keeps running forever, going from one state to the other, and then the whole sequence of states is an infinite collection of information which cannot be encoded into a natural number in any sort of reasonable way. So if it holds, then you should be able to assume this. But what then is really a computation of a Turing machine? Well, it is a finite sequence of instantaneous configurations. And we can encode instantaneous configurations as natural numbers. Therefore, we can encode finite sequences of instantaneous configurations as natural numbers. And therefore, these sort of these computations can be encoded, or partial computations where you just take like these 5 steps in a computation of a Turing machine. So these things are going to be important. That computations of Turing machines, if looked at with these encodings in mind, can mean that the Turing machine takes a Turing machine and a computation of a Turing machine as an input, and it does something to it. Things like that. But these really are surprisingly important observations. So think about them for a moment while I erase the board, and ask me questions if there's any problems. Everybody happy with this? I'm looking at this point for like delighted. It's important enough that you really want to be satisfied with it. So now we know what a Turing machine is. We know how a Turing machine can compute certain things we care about. But you might have lots of questions about, well, you defined this Turing machine in this way. When I was taking this other course, it was completely differently defined, because instead of having the tape be infinite in both ways, it was only infinite in one way. Or you might say, well, in this other course I took, we weren't considering Turing machines with one tape, we were considering Turing machines with an arbitrary finite number of tapes. Or you might say, your Turing machine has as its tape alphabet, the symbols that can appear on the tape, only 0 and 1, and before we could arbitrarily choose this in some other course. And so it turns out that things like number of tapes, tape alphabet, any other things you might want to change?
1 or 2-sided.
Pardon?
1 or 2-sided.
1 or 2-sided? Anything else which I didn't mention, which you wonder about?
Oracles.
Not this list. That matters. Yes, that changes things.
If it has to move left or right, or if it just
number of steps. Of how do you say? Number of moves per step. Sounds a little funny. It doesn't seem to exactly capture what I mean, right?
Types of movement?
Sorry?
Number of types of movement or something like that?
Yeah, like lengths of moves. Can you stay in one spot, or do you add instructions which say move that direction 481 steps and that direction 500 steps? Consider this all number of moves per step. All of these things don't change the notion of computability.
What about number of processors?
What does number of processors mean? If you can tell me how you get a Turing machine with multiple processors, like two heads.
Two Turing machines working simultaneously.
So the answer is it doesn't matter, but I'm not. But that answer is only the answer if the question actually makes sense. And I'm trying to decide how two Turing machines working together, right? They need to have a communication kind of thing. Maybe same tape, right? Multiple heads and things like that. Does not matter. As long as you didn't hear him say oracles, then I can say it. It does not matter. And in fact, it doesn't matter in a very strong sense. Right? We just established, and we'll get back to this later, that a Turing machine can compute sort of Turing machines, other things. And it turns out that if you are considering Turing machines with 481 tapes, then there exists a Turing machine with one tape, which, given a description of your Turing program for the 481 tape Turing machine, simulates it. Not just, that sounds like more was coming, and there might be, but right, there exists a Turing machine of our description which simulates Turing machines using 481 tapes. And so if you can simulate it, then the notion you can simulate isn't stronger than you are. And the other way around, clearly a Turing machine with 481 tapes can simulate a Turing machine with one tape by just ignoring the other tapes. It's a little nicer. It's a little nicer in a way which we won't care about. But for these kind of things, the simulation is with a polynomial time slowdown. So even if you do complexity theory, these things are still the same.
Is that even if the tape alphabet is uncountable?
I'm not sure how you would use an uncountable tape alphabet if you have a finite set of instructions. I think that essentially is a proof that yes, it really doesn't matter, because you can only use a finite part. And so you could say, my Turing machine is of this size, the tape contains all these other symbols, but all the symbols not mentioned in the program are, as soon as the head lands on it, it's immediate halting, so they're all the same, so they don't help you in any way. Yes. But right, the interpretation of this does not matter is exactly that you can write a Turing machine program which simulates any Turing machine which uses 481 tapes on a Turing machine with one tape, and the other way around. And the same with tape alphabet, right? Tape alphabet, and that's even simpler to say, right? If you want to use an ordinary alphabet, you could just use some sort of ASCII encoding on your tape, and ASCII goes into binary, and therefore you can use it. Well, you need to agree where the bytes start and end, but you can agree that. Number of moves per step. Think about it for a moment and convince yourself that if I give you a Turing machine program which uses some instructions like move left 481 steps and move right 481 steps, then you can write a Turing machine program in our alphabet which does exactly the same thing. Because what it does is, one way to do it is to say, okay, you encounter this instruction, now instead of doing this instruction you go to a fresh new state, state 1, and if you're in state 1 reading either symbol, you move left one step and you go to state 2, and if you're in state 2 reading any symbol, you go left one step and you go to state 3, and like you make a nice sequence of 481 fresh states. When you get to the end of it, you have moved left 481 steps and you go to where you were supposed to go in the original instruction. And so all of these things are equivalent, and they are equivalent in ways that are very nice and simple to describe. But things get a lot worse than that. Right? We choose this particular model of a Turing machine for a couple of reasons. It's nice, simple, right? It was a particularly simple description. I took half an hour introducing what a Turing machine is, but that was just because I was very careful about it, right? It's something which, even though the details don't matter, I do want you to understand what it is, because it's rather basic. But it is just one of many models of computation. And if you have one of many models of computation, then you can wonder about the other models of computation. And here, so after I say this, I'm gonna try and quickly do one model of computation which looks completely different. But it has turned out, and this is not a mathematical theorem, this is a historic fact which has been attempted to be disproved sufficiently often that there is reason to believe it, especially because, as you will see in the rest of the course, believing this statement will make your life a lot easier. And whenever you become doubtful about it, you can just say, okay, I believe we're dealing with Turing machines, I'm going to go down some levels of detail and write a Turing machine. But so the church Turing thesis says anything which is intuitively computable is computable by Turing machine. And so, right, what is this based on? This is based first of all on the idea that you should probably have an intuition about what it means to be effectively computable. But what it certainly also means is that if I do a reasonable attempt at defining what it means to be computable, and you do a reasonable attempt at defining what it means to be computable, according to the thesis, we should agree. And so this is exactly where the thesis also comes from historically. Lots of people defined lots of different notions of what it means for functions to be computable, and they look very, very different, and so I'll define one in a moment to show how different they can look. They look very, very different, but any of these other notions that we have encountered so far, as long as they weren't obviously deficient, right? Sometimes you come up with a notion, you think it looks good, and then you start thinking about it more, and you notice, well, I missed something. But any not obviously deficient notions have turned out to be equivalent to Turing machines. Any of these other notions can be simulated by Turing machines, and so we believe this, and this is why I was perfectly comfortable standing here letting you suggest all sorts of change of funny things to do with Turing machines, because I believe this thesis, and I believe that as long as you don't throw me oracles, I can easily make this statement even without thinking too hard about proving it. And one of the things this is going to allow us to do all through the course is not constantly be programming Turing machines, but just look at two reasonable kind of operations, and then whenever you're in doubt you can write a Turing machine, but when you're not in doubt you can just write these reasonable operations and be all happy and merry on your way without dealing with a very long list of 5 tuples, which right, you're not going to get right anyway. Okay. 5 minutes to do this. Can I do this in 5 minutes? Can I do something else in 5 minutes? I can do something else in 5 minutes. I think so. What I want you to show in the book, and you should read this, is the recursive functions and the mu or the primitive recursive functions and the mu recursive functions. That is a definition of a class of functions by saying by giving an inductive definition. Gödel gave this, and he said, well, obviously addition is computable. Obviously projection onto a coordinate is computable. Obviously. At some point he stopped saying obviously. Right? If I have a bunch of computable function and I compose them, then I should still get a computable function. If I do a reasonably simple definition by recursion, and he, right in the book he shows down what the equations are. If I do this and my input functions are computable, then my output function should be computable. And finally he said, a computable process, the following is a computable process. I take a computable function and I look at its output on 0, and then I look at its output on 1, and then I look at its output on 2, and each of those I can compute, and I keep on searching until I find an input where the output is 0, and then the output of my function is that particular input. So you do a search through the inputs till you find one you like. This sort of search is also computable, and so this is very different from Turing machines. Here I'm just describing in an inductive way a class of functions, but it turns out that all the functions in that class are Turing machine computable, and anything Turing machine computable is in that class, and so they are the same again. Okay, so I wanted to finish with the one thing that I think mostly fits in 5 minutes are Oracle Turing machines. So, I'm still doing like the introduction into what's computability about, right? I never progressed really yet past to doing actual computability, and after we have Oracle Turing machines, then I can actually say what I think this course is about. And so the first thing I wrote down over here was the lie. Computability theory is about what computers can do in principle. After we have this definition, we can fix this lie a little bit. So, what are Oracle Turing machines? Well, so let me first introduce a notation. This is, right, we have every Turing machine program can be represented by a natural number. So this gives me an enumeration of all Turing machines. And this notation is, take the Turing machine whose program is in E, give it input X, and see what it computes to, and its output is Y. So this is just a convenient way to write down, if I give the eth Turing machine input X, its output will be Y. And maybe sometimes when you're wondering about halting or not halting, then you would say like, it halts and it goes to output Y, or phi e of X does not halt, which is indicated by an up arrow. One of the things that you could imagine is that you have your Turing machine, and there is a particular set of natural numbers you care about a lot. Let's call this set B. So there's this particular set of natural numbers you care about a lot, and so this is a set of natural numbers. So it's completely determined by yes and no answers to n being in B. Right? 1 is in B, 2 is not in B, 3 is in B, 3 is not in B, and so if you want to fill in the details here, you could say that representing such a set B in the context of Turing machines could be by making it a one-way infinite tape of zeros and ones, which is the characteristic function of this set B. And now my Turing machine using this set B can have this thing on the bottom is what ordinary Turing machines look like. Now it has an extra tape containing the characteristic function of the set B, and now my instructions look like, I don't know, 7 tuples, because you also indicate the head movement on the Oracle tape, and you have an instruction which says, well, look at what you have on the Oracle tape and copy it over to your real tape, something like that. And so I have, for a specific set B, enriched my Turing machine model with access to the characteristic function for this set B. And this is exactly what an Oracle Turing machine is. An Oracle Turing machine is a Turing machine with an additional tape containing the characteristic function, which it can, like, you can move the head back and forth, and therefore always answer questions about whether or not something is in B, even though B could be an extraordinarily complicated set. Okay, I'll leave it at that. Think about this. I've been even fuzzier in my description of this than ordinary Turing machines. Make sure it makes sense.